to lecture 4, at last, of submodular functions optimization and applications to machine learning. We still have the same reading assignment we've had for a while. It's amazing how much stuff he has managed to fit into the first chapter. Although if you want, you can start reading the second chapter. This is announcements that we don't need to go over. Today what we're going to be doing is proving a number of equivalent definitions of submodularity and talk a little bit more about independence, and then begin our discussion about matroids. But before we do that, let's do a little bit of review. So last time we talked about different compositional properties or combining properties of submodular functions. We said that on the one hand, if we take positive linear combinations or conic combinations of submodular functions, we preserve submodularity. Number two, we said that if we restrict submodular function to a set, we preserve submodularity. Number three, we said that if we take the max of a set of items, that's called that's the basis of this facility location function, which is a very popular and common submodular function. That's a submodular function. And then we have the log determinant function, which we know to be submodular. Is this function monotone, the log det? What do you think? Is it always increasing? No. Imagine, for example, a diagonal matrix where the entries are all between 0 and 1. If any of the entries are less than 1, as you increase the number of entries, then you're basically multiplying more matrices, more coefficients less than 1 together and taking the log of that, so you're actually getting smaller and negative. So we also talked about an important property, which is concave over non-negative modular. We said that this function was submodular. And we also identified if and only if conditions. We said that if it's the case that for all modular functions, then taking the concave over modular function is submodular, or taking this function, g over a modular function is submodular, then it's concave, and vice versa. So we need to be able to look at all modular functions in that case. We talked about a composition of a non-decreasing concave and a non-decreasing submodular, preserves submodularity. We talked about taking the min of monotone, either increasing or decreasing submodular functions, preserves submodularity. We talked about that as a consequence we have the saturation function, or the min, which basically truncates or saturates a particular submodular function, and that preserves submodularity. And that follows immediately from the monotone property. And this is an important one because we use that a lot in applications. We defined two different gain notations. We're going to be using this a lot today. F of A given B is equal to F of A union B minus F of B, or if we just have an individual item, F of J given B is equal to the difference. So you should be familiar with this notation now. And we have a couple of other last properties we talked about. We said that any function can be represented as a difference between two submodular functions, number one. Number two, any submodular function can be represented as a difference between a monotone non-decreasing submodular function and a modular function. So here's the monotone non-decreasing submodular function, and here's the modular function. And that's kind of interesting. So that in some sense, all of the structure, all of the dependence structure, or the interaction structure in the submodular function is contained within the inherent monotone non-decreasing submodular function, and the rest is essentially a set of unaries, essentially individual item costs or item values that have nothing to do with the way in which these items interact. And then lastly, we said that as a result, that any function can be expressed as the difference between two polymatroid functions. In fact, that basically means two monotone non-decreasing non-negative submodular functions. And we do that by essentially splitting the modular part into its positive and negative bits. Okay, so now what we want to do is begin to sort of see how we prove the relationships between these. And these are proofs that sort of, like I said last time, introduce some techniques that we're going to be using a lot, and that we'll need to essentially be able to see relatively quickly, because when we get to more detailed proofs, these will be assuming this holds, these kinds of things hold right away. So we have these three different definitions of submodularity. The submodular concave property, which is defined in this way. We have the diminishing returns property, and what, at least in this class, this isn't a very common term, but what we're calling in this class group diminishing returns, which is basically the diminishing returns property but applied to a group of items C rather than a singleton item. Now obviously this would hold if C is a singleton item. Immediately we have that the group diminishing returns property guarantees the diminishing returns property, because this is basically this is a property that is said to hold for all C less than V except for B, including C's of size 1. Right? So obviously diminishing returns hold. But what we want to do is show that these properties are identical to each other. Namely, we want to show that submodular concave is the same as diminishing returns, which is the same as group diminishing returns, are identical. And so what we're going to do is we're going to do this by proving this triage cycle, this this triangle cycle that we have this set of implications, that submodular concave implies diminishing returns implies group diminishing returns, and lastly, group diminishing returns implies submodular concave. So let's start with submodular concave implies diminishing returns. So just to remind you what these things mean, we have their definitions up here at the top. So this is essentially what we're trying to show. Or in other words, we're trying to show that this bit here implies this bit here. Okay? So we're assuming that we've got submodular concave, which basically means that we've got this property. All right? And now what we're going to do is take an A and a B and a V that satisfies this expression. And right away, we have from submodular cave that this is true. Now, the reason why we have this is true is because we have that this and this, when we take the union of that together, that's equal to this, and this, when we take the intersection of that together, that's equal to that, right? Because why? Well, because V is not a member of B, and B is a superset of A. So if we take the union of A plus V and B, we've got B plus V, since V is not in B. And if we take the intersection, the stuff that's common is A, because since V is not in B, and V is not going to be in A either, since A is a subset of B. So then we rearrange this, and we immediately have the diminishing returns property. That the value of V decreases in a larger context. Okay. Okay, that's done. Everybody see that? Very easy. So the next property, it introduces something that's particularly important. So this is, again, what we're doing is we're showing that the diminishing returns property, which is this stuff here, implies the group diminishing returns, which is this stuff over here. Okay. So how do we get that? Well, what we're going to do is we're going to use a vehicle that we're going to use quite a bit throughout this course, which is this idea of telescoping sum. And I thought maybe it would be worth just giving a little bit of an example of what this particularly means. Like, let's say we have, let's say we're just trying to compute 10, let me just use a thinner pen, 10 minus 5. Okay. So that we know to be equal to 10 plus 0 minus 5. Right? Hopefully. And that's equal to 10 plus negative 9 plus 9, negative 8 plus 8, negative 7 plus 7, negative 6 plus 6 minus 5. Right? And hopefully you can see all that stuff. And so then that, we can just rearrange the terms and just write this as equal to 10 minus 9 plus 9 minus 8 plus 8 minus 7 plus 7 minus 6 plus 6 minus 5. Okay, so that's basically the idea of essentially a lot of the methods that we're going to use today. This bit here is essentially all we're doing starting in equations 4.5 through 4.9. Okay, so how do we do this in the context of submodularity? So we're going to use that, and then we're going to use the diminishing returns property on the singleton items, on just the V's, and then we're going to create this telescoping sum to show that it's something that's true about a group. So we start with the group difference. So we want to show that this is greater than or equal to this, right? Because this first thing here is C in the context of A, and this next thing is C in the context of B. It's a bigger context because B is a superset of A. So the way we do this is we start with this green difference here again. And now what we're going to do is all of this stuff here is just that I'm highlighting in green now, that's really just equal to 0. Right? That's just like the minus 9 plus 9, minus 8 plus 8, and so on and so forth. Right? So that's just equal to 0. But now what we're going to do is we're going to rearrange terms. So we're going to put the first term in that big sum, which equals to 0, and group it together with this guy, which is exactly what we did when we looked at this this sum right here, right? We turned it in this, and we're just going to write it in that form, right? And that basically gives us this, right? But now notice that this is essentially a gain form. This is basically this is like the value of Ci. This is the one guy that's different. So that guy Ci is there, but he doesn't live anywhere here. So it's like the value of Ci in the context of A union C1 through Ci minus 1. So you could even write this. I mean, in fact, let's just do it. You could write this as equals the sum for I is equal to 1 to k of f of C of I given A union C1 Ci minus 1. Okay. But now, what are we doing? We're using submodularity and say, well, if we grow in each one of those terms, we can use the sort of individual diminishing returns property and say, well, let's grow the context from A and the partial accumulation of C's to B. And B is going to grow that context as well. So therefore, we get that this is an inequality here. We've just grown the context from A to B. Right? But now we just break things apart, use the same kind of stuff that we did here, same stuff that we did there, and go backwards, and we've got this bit. But now what we'll do is we're left with this, which is just 0 again. And so what we end up with is our final result, which is this. Right? Okay, so pretty easy, right? But that's our first, I think that's our first example of telescoping summation. And we're going to use this a lot. This general property is something that we use a lot in submodular, showing submodular quantities. Yep?
That inequality held because you assumed the diminishing returns.
Yes, so remember, exactly right. So remember, we're assuming this, right, and we're trying to prove this. Okay. So the last bit that we need to do is show that group diminishing returns implies submodular concave. So what group diminishing returns says, just to remind everybody, is that this is true, and this is the gain form of group diminishing returns. You can see how useful this gain notation is. Basically, it allows us to show what we're trying to show in one line. If it wasn't for the gain, there'd be no way we'd be able to fit all of this stuff in one line across the screen, and therefore there'd be no reason to have a course on submodularity. So this is a really important thing. So we have that implies this. Right? So let's assume this. Let's assume this left thing, which is group diminishing returns. And let's assume that A, so we want to show this for any A and B, and let's assume that A is not equal to B, because if A is equal to B, it's trivially true. Right? If A is equal to B, it's f of A plus f of A, it's greater than or equal to f of A plus f of A, which is always true, no matter what, for any function. So let's assume that A is not equal to B, and then make these definitions. We're going to intersect A and B and give us A prime. We're going to subtract B from A and get C, and we're going to set B prime is equal to B. And so what we get is, since we have this group diminishing returns, so notice that A prime is a subset of B prime now, right? Because A prime is A intersect B, and B prime is B, so therefore A prime only contains what's common between A and B, whereas B prime is all of B. And so therefore we immediately get the group diminishing returns property, because that's what we're assuming, right? But now we just rearrange the terms, put all of the positives on one side and the negatives on the other side, and we get this. That's just basically, if that's not clear to you, just put this over here and put this over there. But now let's look at what the definition of A prime plus C is. So A prime is A intersect B, and C is A except for B. So this whole stuff is just equal to this. We've got these things are the same, and these things are the same, and then lastly this is the same, just by the definition. And so then A intersect B plus A except for B is what? That's just A, right? We take the intersection with B plus the residual, that's A. And then B is already B, so that's just A. F of A down here. F of B is just this. And this stuff is going to be equal to the union of the two. So if we take B plus the stuff in A not in B, that's the union. And then A intersect B is just the intersection. So therefore we've got the submodular concave definition. Okay? Any questions? Yep.
Okay, so just as a clarification I'm asking, in this scenario, B is a subset of A, not the other way around.
A prime is a subset of B. So we're not assuming anything about A and B.
No, is it that because we are saying that C is A minus B, and that cannot happen unless it's an empty set or B is a subset of A?
No, so all we're saying is that A is not equal to B, and C is the residual of A except for B. That's all we're saying. We're saying that C contains that which is in A but not in B. Right? Think about it from the set theory. So I'm not going to explain a lot of the set theory stuff, but I hope that... So what is C? C is going to be all of this stuff. C is all this stuff. Okay, that's all we're doing. So in general, if you're not sure about set theoretic properties, or what even A slash B means, just draw the Venn diagrams. It makes it much clearer. So most of the time I'm not going to do it. I'll do it a little bit for you, but I think you should be able to, if you draw the Venn diagram, sometimes you need 3 sets, and you look at these intersections and differences and everything, you can immediately see that it's true. Okay? Any other questions? Okay, so there's another definition of submodularity. In fact, we're going to see that there's quite a few of them. This one, I don't know, for whatever reason, I'm calling it singleton or 4 points. These aren't standard names for these, but we're just using it for the context of this class because there hasn't historically been a place where all of these different definitions have resided together in one place other than this class. So we need to name them, and these are the names that we're using. So this is, let's call it the 4-point submodular definition. And it's basically saying that a function is submodular if for any A and any lowercase ab not in A, namely, these are elements, and this is a set, we have this plus this is greater than or equal to this plus this. Now, right away you see that submodular concave implies this, right? Because basically we have that if we take the union of these two, we get this. And if we take the intersection of these two, we get this. Right? So this is union, and this is intersection. Don't you like these graphics? Every time I see these graphics, I'm reminded of like a candy store. So this is submodular candy. So it follows immediately from diminishing returns. To achieve, well, actually, it also follows from diminishing returns. I guess it follows from any of the ones. So it follows. It's very trivial consequence of the definitions we already know to be equivalent. To get the actual diminishing returns definition, what we do is let's just take any A which is less than B, and take some, and let's just name the items in B that are not in A. Okay, so these are the items. So the idea is that there are K items in B that are not in A, and these are their names, B1 through BK. So what we want to do is we want to show that this is greater than or equal to this. So we're going to do it one step at a time. Similar in concept to the idea of the telescoping sum. We do a lot of this stuff one step at a time. So the first thing to do is we can get this is greater than or equal to this. Now why does that yellow bit hold? No, from 4 points. It follows from 4 points. It's exactly this, just rearranged. Right? Because this, take a look at this. So this is the same as this. Right? This is the same as this. This is the same as this. And this is the same as this. Right? So now what we've got is this stuff in yellow, and we just do it one more step. So we apply it again. So why then does this next inequality hold? Why does this yellow stuff hold? Exactly. We treat A as A plus. It's the same thing. It's equation 4.14, but treating A as A union B1. Right? And now B2 and A become the two guys, A and B. And then we keep doing this until we keep doing this repeatedly until at last we're at this guy where, oh, look what we've done. We've now added to A all of the stuff in B that makes it B, right? Namely, we've added B except for A, and then now this A belongs there, and this stuff belongs to B, and this is just B here. So therefore, we've achieved the goal. We've achieved diminishing returns. So now sometimes this is useful. I mean, sometimes it is useful to see and to gain a really deep intuitive understanding of submodularity. One needs to see why all of these definitions are true.
Is that called a 4 points definition? Is it just because you're evaluating it at 4 points?
I'm calling it 4 points. Like I said, these are our names in this class. You won't go out and see them, but I'm calling it 4 points. We're calling it 4 points because it's evaluating in 4 points. And it's inspired by the 4 points property of certain, it's from information theory. But it's just touching it on 4 points. I mean, you can also sort of see it as a square in a hypercube. So like this is the empty set. This is A, this is B, and this is A plus B here. And so what we said before was that this diagonal, or the sum of these two, let me just do it a little bit more accurate. So this point and this point have to be, summing together have to be greater than or equal to this point or this point. And so what are those 2 points? Well, that's basically this point and this point have to be greater than or equal to this point plus this point. So that's how we get it. 4 points. But it has to be true for every one of these squares or diagonals or partitions. I mean, it's not just there are lots of different instances of this. So it needs to be for all A and for all uppercase A and for all lowercase AB. And that defines a lot of different bits on the hypercube. When you are in an n-dimensional hypercube, there are a lot of things to check. But we'll get at a little bit at some graphical definitions of submodularity in a bit. So I'm not going to go over this, but if you want, if you want sort of a direct proof, like one-page proof that submodular concave and diminishing returns are the same, here it is. So since we already have proven this indirectly through this group submodular group diminishing returns, I'm not going to do this again, but this is sort of a nice little simple, also using telescoping sum and using the gain notation. And again, thanks to the gain notation, we can fit this proof into one page. So please go over this offline. Okay, something else that you might find interesting. So let's say that you've got a submodular function, and then you've got two sets, C and D. Now remember, just so that there's no confusion, I'm switching between E and V as the ground set. Sometimes I'm using V and sometimes I'm using E. I hope that there is no confusion associated with that. I will never use either V nor E as a subset. So in other words, there will never be a case where V won't be a ground set or E won't be a ground set. However, I will be taking subsets of either one. And like I said, hopefully there won't be both ground sets in the same equation. If you see that, then that's a bug. Okay, so we've got two subsets, C and D, and we have that one of them is contained in the other. Okay. Now, thanks to the submodular property, we can take this difference, and regardless of which one is contained in the other, we can get a lower bound on that difference. And that's just, I thought it would be kind of interesting. Like, for example, let's say that C is contained in D. Okay, so if C is contained in D, that means that there's some x such that D is equal to C union x. Now let's take any x for which this is true. There can be a lot of them, right? Because, obviously x can contain none of C or all of C or everything in between. So there can be 2 to the size of C of such x's at least. I think exactly, actually. So let's say that D, any of those x's such that D is equal to C. So then we take this difference, f of C minus f of D. That's equal to f of C minus f of the union of C union x, which is just definition of D. But then we use this, the submodular concave inequality to get this. Okay? So that's a difference. That's a nice lower bound of the difference. Okay? Thanks to submodular concave. We can write this using gain notation. And this sort of is an interesting looking equation, which actually turns out to be something that also defines submodularity. It's basically f of C union x given C is less than or equal to f of x given C intersect x. So in some sense it says, like, given C, the newness of x considered with C in the context of C is never more than the newness of x by itself in the context of the intersection between C and x. Okay. Now I said that it doesn't matter. C or D can be contained in each other. Let's say instead of C contained in D, let's say that D is contained in C. So if D is contained in C, that means that we can write D as the intersection between C and some y. In fact, there's lots of y's that have that property. That when we intersect it with C, we can get D. Right? In fact, all of the y's, obviously, y can't contain anything less than D, but it can contain more. And so any such y that has that property, we can write this difference as f of C minus f of the intersection, which again comes from definition. But again, from submodular concave, we get this. So again, it's a lower bound. It's a difference lower bound on the difference, f of C minus D. And again, it's a different lower bound, but still we can lower bound the difference between two sets if there's a containment relationship between them in any submodular function. This is something that's useful sometimes in proofs. And so that basically corresponds, if we look at this, in the gain form we have this thing. And notice that that and that are the same. I mean, there's no difference really. So it's the same sort of property. Now, in fact, there's lots of definitions of submodularity, and here's a one-page summary of them. So this is the, yeah.
So, yeah, what is 4.2 exactly saying?
Sorry, say again?
What is 422, what is it saying?
What is 422 saying?
Intuitively, what is it saying?
Yeah, so let's think of these as like, think of it as like an information function. So it's saying that if you already know C, then the additional information given by C and X is never going to be more than if you know the common information, at least in the common index between C and X, of the information of X. Right, so that's the submodularity property. That's another way of looking at the submodularity property. The reason why we look at these different pithy inequalities is because each gives us sort of a different angle of the intuition of what submodularity says and what it doesn't say. Now, for your problem sets, you're going to be, coming up with examples of subadditive functions that are not submodular and submodular ones that are, negative, and you're going to be coming up with examples of all sorts of things that will help with this. But here, by looking at these inequalities, we can begin to gain some intuition. Okay. And if you're worried, remember this is just the submodular concave definition rearranged, and this is just writing it in gain form. Right, so this is really just submodular concave restated. So even like when I go to this next page, I'm not going to restate it again because that's just arithmetic to get that to this. Right? So it's so trivially the same. So we've got submodular concave 4.25. We've got the diminishing returns. We've got group diminishing returns. We've got the 4 points property in gain form. This is 4 points in gain form. Here's an interesting one, I think. I don't know why I find this one interesting, but for some reason I do. This one says that a function is submodular if and only if it's conditionally subadditive. So what do we mean by subadditive? So remember, again, if we just ignore this stuff that you're conditioning on for the minute, if you just ignore that for a minute, It's a different inequality, but just ignore it. That's the definition of subadditive, right? You're basically saying that f of a plus f of b is greater than or equal to f of the union. When you add them together, the value of the things added together, or the value of the things union together, is less. The whole is less than the sum of the parts. That's the subadditivity property. But that's a subadditive is not the same as a submodular function. A subadditive function is different. What a submodular function is one that's conditionally subadditive. You have to condition on the intersection using the gain form. And a function is submodular if it and only if it's conditionally subadditive. Here's one that's interesting. Let's say that you take any two sets, S and T. This one is, has been, as you'll hear later in the course, particularly important for some recent work by our group in machine learning. You'll see why later in the course. But this is an inequality that basically says if you've got any two sets, S and T, that, let me draw a picture. Okay, so let's say you've got S here, and you've got T here. Okay, so it's saying, actually no, let's put S over here and T over here. Okay, so so there's no relationship between S and T, right? So they're arbitrary. So basically it's saying that f of T is upper bounded by f of S plus stuff that's in T but not in S. Oops, that's the wrong set. Stuff that's in T but not in S minus stuff that's in S but not in T. And notice that we're summing, so it's like the sum of singleton elements. And those colors on the screen don't look any different. But if you are watching this on YouTube, you'll see beautiful yellow and beautiful on the left and beautiful green on the right. So that's really too bad. But in any event, what we can do then is, now what if it was the case that, say, S was really a subset of T, right? So basically, if S is a subset of T, then basically it would mean that all this stuff over here doesn't exist. So it means that that doesn't exist. And if that doesn't exist, then we just got this equation here. Right, that's just basically just f of T is less than or equal to f of S plus the stuff that's in T, sum over the stuff that's in T, not in S. So we can see that these two equations, 4.30 and 4.31, sort of go together. And there's two other forms of this equation. There's 4.32 and 4.33, which also go together. Which now what we're going to do is we're going to prove some of these. We're going to prove that I think that's the last one. Hold on, let me just check. That's the last one. So what we're going to do is we're going to prove that 4.28 is equivalent to 4.30, and that's equivalent to 4.31. Now 4.28 is already a definition of submodularity. So what this means is that, of course, 4.30 and 4.31 is also a definition. In fact, they're all equivalent. All of these things are equivalent. Now, you might think, well, why do I care? Using different definitions can have profound differences in the implications of the properties. You know. So, in other words, this is a fundamental, if and only if necessary and sufficient set of conditions for submodularity, which means that you can use this stuff. It means that, well, this is something that's true. You got a submodular function, you've got this stuff. So how do we prove this? Let's go on. Are there any questions about this? Like I said, 4.30 and 4.32 are particularly useful, as you will see. So the reason why I'm spending time on this is because of their utility. So now we've already seen that 2.5, 2.6, 2.7, 2.8, and 2.9 are the same. So that's these guys, 2.5, 2.6, 2.7, and 2.8, and 2.9. We've seen that these guys are all the same. Actually, we didn't do the conditional subadditivity, but conditional subadditivity, I think you can see pretty readily, is the same as submodular concave. Just terms cancel out, and you get back submodular concave. But what we want to do is we want to show that 2.8, 3.0, and 3.1, and 2.8 are the same. So what we're going to do is we're going to show that 2,8. Let's do it this way. We're going to show that 2,8 implies 3,0, which implies 3,1, which implies 2,8. Let me just give you a minute to just parse these. Just stare at them for like 15 seconds or something. Okay, it's probably about 15 seconds. And to show them, it's actually an interesting way. What we're going to do is essentially, we're going to start with f of s union t. So it's kind of like we have s and t here. And it's like the value on everything, this is the value on all this stuff together, is going to be equal to, I mean, we know that from the gain, it's equal to the value of s plus the value of t except for s, right? But what we're going to do is we're going to start by upper bounding that stuff, upper bounding the pink stuff. And then similarly, what we're going to do is do the opposite. I wish I could flip this backwards, but what I can do is just flip these guys and say that this is s and this is t now. So this is going to be the value of t plus the value of s given t. And what we're going to do is we're going to then lower bound this stuff. And then when we combine the upper bound and the lower bound, what we're going to get is we get this property here. And then that allows us to solve for f of t is less than or equal to f of s plus the upper bound minus the lower bound. And that's how we get it. Okay, so is the general approach clear? Okay, so first we're going to do this upper bound, I believe. So we need to define some notation. Let's say that the stuff that's in T but not in S, let's call it J1 through JR. So that basically means that T has R items that are not in S. And similarly, the stuff that's in S, not in T, is K1 through KQ. And so that means that S has Q items that are in S but not in T. Okay, so the first thing we're going to do is we're going to upper bound the gain of T in the context of S, which is basically this stuff. So all we're doing is we're here. We're going to show this bit and this bit. We're going to show this upper bound. So the f of s is the same. We're not touching f of s, right? So this is f of f. This is the gain right here. So that's equal to, it's one of these things where we've added a big giant zero, a form of zero, right? Does everybody see this? So basically it's the very first term, the left term on the left element of the first term is just basically f of s union t, and the right element on the last term is just f of s, and we're just adding and subtracting the same number in each case. And so then that can be written in gain notation. Notice that each one of these, it's basically the gain of jt in the context of S union J1 through Jt minus 1. Okay. But by making the context smaller, by essentially crossing all this stuff out, we get an upper bound of each one of those terms. And now let's just write it in the form that we want. Well, we're just summing over the items in T, not in S. So therefore, what we've got is this property here. Now, this is a really common property to those of you who are familiar with information theory, because it basically says, if this is the entropy function, it says that the conditional entropy is upper bounded by the independence bound. That's basically saying, the set of random variables T, when you condition on S, the entropy of the sum of the entropies of the random variable, which would be the assumption that basically S renders all of the random variables in T independent, that's going to be an upper bound. Or if S is the empty set, it's just basically the independence upper bound of the entropy. But here it's true of of any submodular function. And it's again, it's conditional. It's the one that's conditioned on S. So this is not a surprising, for those of you familiar with information theory, it's not a surprising bound. If you're interested in machine learning, by the way, I think you should know information theory. So if you haven't taken information theory, I think it should be one of the core classes that all machine learningists know about and take. It's used widely in machine learning. Okay, so next what we're going to do is we're going to lower bound S in the context of T. So here what we're doing is, again, we're, what should we erase? So what we're doing is we're showing that is lower bounded by this stuff, and so we need an expression for this stuff over here. Okay. So how do we do that? Well, it's the gain of S in the context of T. So again, we're writing it as a sum with a bunch of zeros in it, right? So remember, it's like the first term plus 0 plus minus the last term, where we've rearranged the terms. Remember the 10 minus 5 example? It's exactly that. So it's the 10 minus 5 example, except that we're already writing it as a set of as a sum of differences. So they're not explicitly mentioning the 0. So now notice what's happening here. So we're saying that this is a little bit interesting, because we're saying, okay, well, the context, it's the gain of, what color should we use? Let's use green. It's the gain of KT in the context of T union K1 through KT minus 1. But we're writing K1 through KT minus 1 as K1 through T subtracting off KT. Okay. It's perfectly fair, right? Mathematically right. But why do we do that? Because what we want to do is say, well, in the next step, when we actually show the inequality here, let's continue to subtract off KT minus 1, but now grow the context from K1 through KT to all of S, right? Now here's K1 through KT, right? And that's definitely going to be a subset or equal to S, right? Since all of K1 through KT has to be a member of S. It can't contain anything in T, but it has to contain all of S, or it has to be inside of S. In other words, this is a subset of S. So when we grow the context to S, this basically means that this inequality holds here, thanks to submodularity. But now let's just write it again in set notation, where we're doing it. So now we've got this nice summable lower bound on f of S union T minus f of T. Whoops, that's not what we want to do. Okay, so we've got this upper bound here. We've got the lower bound here. So we've got it in this form. And then we just write f of t is equal to f of s plus the upper bound minus the lower bound. And we're done. We've got the equation. Okay, so now the last thing to show, is any questions about that before we... Any questions? So the last thing to show is 4.30 implies 4.31. Or actually, no, the last thing to show is 4.31 implies 4.28. We've already done 3.0. 3.0 implies 3.1, obviously. We want to show that, 3.0 implies 3.1 trivially. We want to show that 3.1 implies 2.8. Are there any questions about 3.0 implying 3.1? I wasn't planning even to talk about that. Okay, let's look at 3.1 implying 2.8. If I can get back to where we were. Or 3.1 implying 2.8. So basically, what we're going to do is so S is a superset of T in this particular case, and this particular superset we're choosing is going to be S plus these two items, J and K. And so J is not a member of S union K. So we've got 4.31, and we've got this stuff, which is T, is less than or equal to f of S plus these two gains. And then here we're just writing out the definitions of the gains. And then what we do is cancel this and this out to get this, which we can write as this gain, which comes from this, and this term here, which is the same. So basically we're done now. I mean, basically we've got, when we bring this over to the left-hand side here, we've got this, which is the gain of J in the context of S union K, which is less than or equal to the gain of J in the context of S. So hence, we've proven it. Okay, any questions? Okay, no questions? Yeah. This one? This one.
Yeah, I guess the start of this.
Which one?
Not this one.
This one?
Yeah.
Or there's the upper bound or the lower bound?
The first slide where you showed methodology.
Sorry, the methodology or the listing of equations? This slide?
The next one.
This one.
Yeah. So what do you get the first equation? Testing equation.
How do you get the first equation?
Leo upper bound. Just the.
Oh, how do we get this guy?
Yeah.
Okay, so what is f? Let's write this one in yellow. So we have f of t given S is equal to f of t union S minus f of S. Right? So we just, this and this bit and this bit cancels out. And so we're left with this, which is the same as that. It's just that by definition of the gain. I mean, this is the thing. So the gain, whenever you see a gain, it's really a difference. Just remember the gain, and this is why we're using these grouped gains. I personally really like this notation because I find it very intuitive, but then on the other hand, I come from having thought about information theory for a while, and entropy, so it becomes, to me, it's very intuitive to me, just this gain, it's like conditional entropy. But I think that it's in general useful. And like I said, the most important reason to use it is that it cuts down on the world's ink usage. So, okay, any other questions? So that's a good question, so thank you for asking that question. Are there any other questions? Okay, so let's move on. What time is it? I guess, let me see. Let's answer this question first before we move on. So the question is, and I've been calling this submodular concave, why do we even call it concave? Like what does concave have to do with this? Here's sort of the reason why. So whenever we have a multivariate function, a function from Rn to R, we say that it's concave if its Hessian matrix is non-positive definite. Namely, this is the notion, the notation that we use to indicate the non-positive definiteness of the Hessian of f, right? So if we were to define a notion of gain, if we were to define gain as a derivative, in some sense a discrete derivative, so it's like the derivative of b evaluated at a, and it's equal to this difference. And we can actually write it as f of b given a except for b. So in other words, it allows for a and b to intersect, it allows for anything to happen. So this is a discrete derivative. So it's a derivative of a in the direction of b, derivative at a in the direction b, right? So then By the way, if it is the case that there's no intersection, then we have a slightly simpler definition, and it's just f of b given a. So now what if we take a second derivative? What if we take the derivative twice? So we apply the derivative of f with respect to c, and then take the result of the derivative of f with respect to b, and then take the result of that and take the derivative of f with respect to c, and then evaluate that at a. Well, we get this first. Remember that a is the argument, and so then we take the derivative of that with respect to c, and we get this result. Okay, and you'll have to believe me about why that's true if it's not clear. But basically, it should be clear that this is in fact what you get. Okay. So now, if we were to say, well, maybe we could put some some condition on that, like maybe a negativeness of the Hessian-like thing on equation 4.55, and maybe that would give us the submodularity inequality. So let's take a look at that idea and say, well, here's that second derivative, 4.55 repeated, but now saying what would hold, what must be true if it's the case that it's always non-positive. So this is the non-positive condition here. So rearranging terms, we get an equation that looks almost like it. It's f of this stuff plus f of this stuff is greater than or equal to f of this stuff plus f of this stuff. Now, in order to show that this corresponds to submodular concave, we need to show that the union of these two is equal to that, and the intersection of these two is equal to that. So how do we do that? Well, let's just define A prime to be this bit, define B prime to be this bit, and then it turns out, in fact, that the union and the intersection correspond precisely to the union and intersection of A prime and B prime. So, therefore, the function, that definition of the function is kind of like a concavity condition. It's kind of like saying the second derivative is non-positive. If you want sort of a set theoretic proof of this, basically saying here's A, B, and C. These are the original A, B, and C's and their corresponding intersection properties. And then we're defining A prime to be A union C except for B, and B prime to be A except for C union B. And so if we sort of outline those guys, here they are. So here's A prime and B prime in black. If we take the union of A prime and B prime, you'll see that you have everything, right? If you take the intersection of A prime and B prime, what we've got is this bit over here, right? And that's basically A except for B except for C, which is what we want. And critically, A prime and B prime can be set up to be anything, right? There's no restriction on A prime and B prime. We can choose A, C, and B to give us any A prime and B prime. So therefore, it's the same condition. Now, there's a little bit simpler of a way that you can associate submodularity and concavity, which is by using the 4 points or the singleton definition. So here's again the 4 points definition of submodularity. It basically only requires x and a j and a k. And I think we need to do, this is v except for x, right? So it gives us a slightly simpler notion of concavity by defining this derivative. This is, again, one of the forms of the gain that we wrote down. And this is why they use this derivative, or this gradient notation. It's like a gradient form of the gain. So the gain is kind of like a gradient. And then if we take the second derivative, if we take the derivative with respect to k and the derivative with respect to j and evaluate it at x, that's less than or equal to 0. That's identical to the 4 points definition of submodularity. So it's again like a concavity condition. Okay, so this is a good time to take a break. Are there any questions at this point? So this is, this may seem like a lot of information. Raise your hand if this seems like a lot of stuff. Okay, that's good because I think that it will begin to introduce you to some of the methods and the proof techniques that we're going to be seeing throughout the quarter. So let's, if there are other questions. There were no questions. Are there any questions? Should I ask a question? Okay. Why is this lecture so interesting? Well, the answer to that is because submodularity, here's a quote from Satoru Fujishige, and he said, submodularity is forever. That's something that he said to me about a year and a half ago, personally. And I agree with him because I think you find it in so many different contexts, and it's so ubiquitous, and it's so applicable, yet at the same time it's so mathematically deep and rich and beautiful. So that's why this is so interesting. Okay, welcome back to the second half of the lecture. So what we're going to start doing is, as you can see perhaps from looking at the very, very top of the screen where it shows where we're going as well as where we've been and where we are, is we're going to start talking about independence, and we're going to lead to matroids. And as some of you probably have heard me say before, I don't think that one can really understand submodularity well without having at least a reasonable understanding of what matroids are and what they can do. Not to mention that from the perspective of applications, certainly in machine learning, matroids often offer a very, very rich set of possible constraint sets that one can utilize to solve problems of interest. Matroids are very rich. So let's begin to gain our understanding of that. And we're going to spend the rest of today's lecture and Monday's lecture on this topic, possibly Wednesday as well. So remember the rank example of a matrix that we gave, I think 2 lectures ago. So we defined this 4x8 matrix, and we had an index set V, which were integers corresponding to the indices of the column vectors, and we defined the rank function as a function of subsets of that V, which corresponded to the rank of the subspace spanned by the vectors indexed by the set given in the argument to the rank function. Right? So that's the rank function. And we also saw, like I showed before, that there's the rank function of this matrix is a submodular function, and we saw it graphically, and that's what led us to this nice Venn diagram picture. So let's talk a little bit more about this rank function. So it's a function from 2 to the v to the non-negative integers, which is z plus, right? Notice that the rank is never greater than the size. So you can never have you can never span a space greater than the size of either the row or the column size of a matrix, and so therefore you can never be greater than the column span. And that's only the case that it's equal to the size if it's the case that the vectors corresponding to the indices in A are linearly independent, and that's when the rank is equal. Okay, so it's integer valued, it's upper bounded by A, and it's equal only for independent sets, for independent sets of vectors. And if it's the case that A and B are 2 sets that have the rank equal to the size, but let's say that these sizes are different. Now notice that we're not saying that one is a subset of the other. We're saying that the size, the number of vectors A is less than the number of vectors B, but both sets of vectors are independent. Okay? So what it means is that there's some subspace spanned by the set of vectors indexed by B that's not spanned by the set of vectors indexed by A. So there's some vector there that's pointing in a direction that's outside of the subspace spanned by the vectors in A. And so therefore we should be able to, just by having this size knowledge that the size of A is less than B, we should be able to choose some vector in B that will span a new direction. That'll increase the number of subspaces that we're spanning. All right? Everybody get that? So I'm just thinking about it in terms of linear space. So to stress this a little bit further, I mean, again, we're saying that the size of A is less than B. We're not saying this. We're not saying that A is less than or equal to B. In fact, let me highlight that, not in green, but let's highlight that in the only color I have that's closest to red. There's no way of highlighting in red in this program, unfortunately. Or maybe there is, actually. Maybe I could do this. Okay, let's try it. Oh, there's red. What I just said was wrong. Okay, so here's red. Okay, great. For you, it doesn't. You in the class have no idea what I'm talking about because everything looks like either dark gray or light gray. But if you go back and watch the YouTube vectors, you will know exactly what I'm talking about. In any event, is everybody clear on this point, that size of A is less than the size of B? So then the property that we're saying exists of columns of subsets of columns of vectors of a matrix is the following: that if we have A and B whose ranks are equal to their size. Oops, I don't want to highlight that in red. I want to do this one in green. Then, and if we have the size constraint, then that basically means that there exists some index in B that if we add it to A, it increases the rank because the number of subspaces increases. Right? And it turns out that's sort of like a fundamental property. Turns out that's property of a linear space, but that property will be one of the properties that can be used to define everything that you need to know, almost everything you need to know about a matroid. Except it doesn't need to be the case that there's some underlying linear space from which the rank function comes from. So here's an example. Let's say that we've got a graph. And here's the graph down here, right? So it's a graph with 8 vertices and 12 edges. Okay? And we can construct an incidence matrix from this graph. And the incidence matrix is a matrix that has the rows corresponding to the vertices and columns corresponding to the edges. And basically, there's a 1 in a particular row column depending on the edge structure. So, for example, like let's take edge number 6. So it has a 1 in row 3 and row 5. And so then if we look at edge 6, we see that it's connecting vertices 3 and 5. Okay, so it's just basically an incidence matrix. And so what we're going to do, however, is we're going to do a slightly different version of the incidence matrix. We're going to essentially orient the graph, which basically choose any directions of the edges. We're not saying it's a DAG. We're not saying there's no directed cycles or anything. We're just saying take any particular orientation you want, and then represent the orientation by an incidence matrix which rather than just has zeros and ones, has zeros, ones, or negative ones. So remember, well, I don't know if actually we define this. So E plus is the tail, and E minus is the head. So this is the head, which is E minus, and this is the tail, E plus, of a now directed edge in E. And so what we do is we create an incidence matrix where the entry at row V, column E, is 1 if that vertex corresponds to the tail of the edge, and it's -1 if it corresponds to the head of the edge, and 0 otherwise. So here's the head of the edge. Okay. So here's a particular orientation of that matrix that we just saw, and here's an instance of it. So let's do the same column that we did. So column 6, and it corresponds to 3 and 5. So it's this one. So 3 has a negative and 5 has a positive. So the negative one goes on the head. Okay. So everybody clear on that? So it's a matrix representation of a directed graph. That's a very standard way of doing this. Now let's consider 2 things. Let's consider taking subsets of column vectors and looking at their span of this particular kind of matrix. And also take a look at the graph and look at spanning trees of subsets of edges. Okay. So if we take one particular edge, which is edge 1, which corresponds to column 1, we see that the rank of the space spanned by this one column is 1, and then the spanning tree of this one edge is 1. Right? If we take columns 1 and 2, which corresponds to edge 1 and 2, which I don't know if you can see them very well, but it's these two, then the rank is 2, and the spanning tree corresponding to those two edges is 2. Right? I mean, in fact, the edges themselves are already a tree, so there's no, the spanning tree is of itself. And similarly, if we take these 3 columns, the first 3 columns, we have these 3 edges and these 3 columns, the rank is going to be 3. Similarly, if we take these 4 columns, 1, 2, 3, 5, that's 1, 2, 3, and 5, the spanning tree, the edges that we've chosen correspond to a tree. Remember, there's no cycles, that's the only thing that's required of a tree. And the rank is going to be 4, and the spanning tree size is going to be 4. If, however, we do the following, we take columns 1, 2, 3, 4, and 5. So we take edges 1, 2, 3, 4, and 5. We know that we've introduced a cycle. So from the graph, we can say that any spanning tree, of these edges that I've highlighted is going to be of size. How many edges are going to be in a spanning tree, a sub-spanning tree of the edges that we've chosen? 4, right. So no matter what spanning tree it is, right, because we can't have a cycle in a tree. So therefore it's 4. And similarly, we're going to see that the rank of that particular matrix is 4. There's a linear dependence in here. And the reason why, if you can see it, is like x4 is equal to negative x1, minus x1, minus x2, minus x3. That's the linear dependence. And so in general, basically, whenever the edges in the graph specifies a cycle, there's going to be a corresponding linear dependence between the corresponding vectors in the matrix. And so what this means is that if you've got a graph, it doesn't have to be a connected graph. You can have multiple connected components. But basically, whenever you have a spanning tree, which is a graph, or whenever you have any kind of tree, it's going to essentially correspond to linearly independent vectors. Or whenever you have a forest, it's going to be a set of linear independent vectors. But whenever you have a cycle, there's going to be a corresponding dependence somewhere. And now, what if we just start from a graph and we say, okay, let's just define the rank function on subsets of edges of a graph. Is just going to be the size of the largest forest in the, and then the language we're using is the A-edge-induced subgraph of G. So it's a subgraph, right, because it's not all of the vertices, but what we're doing is we're taking a set of edges, and we're taking the set of vertices that are incident to the set of edges A that we're choosing, and then we're taking all of the edges that lie within, that have both of its vertices in that set of vertex sets, and then we take a spanning tree of that result. And that's going to be, and then the size of the spanning tree, the number of the edges in that spanning tree, that's going to be the rank. So the rank of the entire graph is going to be basically a spanning forest of the graph, or a spanning tree if it's a connected graph. And we know that the size of a spanning tree is equal to m minus 1 if it's a connected graph. Right? We also know that the size of the, if it's not a connected graph, of a spanning forest is going to be m minus k. Or sorry, did I say n? I mean n minus k, where k is the number of connected components in the graph. Now, one thing to note right away is that if we take subsets, notice that this function, remember we're taking a constant minus k, where k is really the number of connected components. And remember, that's a supermodular function, so we're taking a constant minus a supermodular function. That's going to give us a submodular function. So the rank function from this graph is going to be a submodular function. But on the other hand, we can see that this rank function corresponds precisely to the matrix rank function that we saw by constructing this incidence matrix from the graph. Okay, any questions? So as we will see, this is 2 ways of defining a matroid. Now, matroids, spanning trees, probably many of you have learnt in undergraduate computer science classes, correspond a lot to the greedy algorithm. Now, we haven't really mentioned that much the greedy algorithm in this class, but the greedy algorithm and greedy procedures is inexplicably, or not inexplicably, that's the wrong word. It's very intertwined with the notion of submodularity, the greedy algorithm. So here's, for example, 3 algorithms for the spanning tree. So these are these algorithms that you learn about in undergraduate classes. You've got a weighted graph where the edges are weighted based on some non-negative weight function, W. Now we know from the terminology that we've just learned that we can think of this as a modular function defined on the edges of the graph. Because when we've got a set of edges, a subset of edges, and we want to weight that set of edges, we just sum the edge weights. So it's modular in the edges. And the goal is to find, say, a minimum cost spanning tree. So let's say it's a connected graph, and we know that there's n minus 1 edges, but we want to find the set of n minus 1 edges that is of minimal weight. Okay. And here's the cost of the tree. So we want to minimize the cost. Usually when you name it cost, you want to minimize. When you name it value, you want to maximize. So it really... and there's 3 algorithms for doing this. There's Borufka's algorithm. And what this one does is basically starts with essentially a set of edges that are going to constitute the spanning forest, spanning tree if it's connected. And what we do is while this resulting graph is disconnected, this is in the spanning tree case, and we look at each one of these components and we add the edge that connects to the component that has minimum weight out of that particular component. Right, so each one of these components, and we look at them and say, oh, well, look, this is, the component can have lots of edges out of it, but we take the one that has minimum weight out of that particular component, and we connect it to the other, whatever component it's connected to. That now becomes a merged component. So there's a greedy nature to this right away, because we say, well, we're taking whatever it is that it looks now, we're taking the one that has least cost. We're taking the one that looks best at the moment, whatever costs least. That decision, in general, the greedy decision in general doesn't guarantee you anything. Because if you're greedy, everybody knows that being greedy is bad, right? Unfortunately, life is not a submodular function. We're supposed to be generous, right? But in this particular context, when you're trying to design a spanning tree, minimum cost spanning tree, being greedy is beneficial. Here's another algorithm. Again, it's very related. It gives you exactly the same answer for the minimum spanning tree problem. It basically, we build up this tree, and we keep adding edges to the tree that have minimum weight edge extending the tree to a new vertex. So it has to be a tree, right? We can't create any cycles. This is Prim's or Dijkstra's algorithm, or Yarnick's algorithm. And then lastly, there's Kruskal's algorithm, where what you first do is sort the edges in increasing order, and then you keep adding edges in that order as long as you're not creating a cycle. So obviously it's very similar to Prim, but there's a little bit of difference here and there. But the point is that in each one of these cases, you're being greedy. You're choosing, you're sort of choosing best whatever looks, choosing next whatever looks best. They're all also, they can find the optimal spanning tree. So in each of these cases, the spanning tree that you're going to get at the end doesn't suffer from being greedy, which is not true in general, but it is true in this particular case. They're also all lower order polynomial times. Greedy algorithm is a very, very efficient algorithm. And like I said, they're all greedy. They have this is sort of the general property. Add next whatever looks best. That's the property of all greedy algorithms. And then they'll always find a basis. Namely, they maintain a tree. They'll find if it's a set of column vectors of a matrix, if you keep adding an element, you're always going to essentially find a maximal linear independent set of vectors. Because at some point or another, you're going to get to the point where no matter what you do, if you add a vector, you're going to get a linearly dependent set. But if you keep adding, if you're greedily looking, it doesn't matter the order in some sense that you choose linearly independent vectors. You're eventually going to get this sort of independent vectors that span the underlying space, or span the space spanned by the matrix at least. Okay? Does everybody see that? So sort of jumping between the matrix case and the spanning tree case. Now, interestingly enough, I mean, you, again, in your undergraduate computer science classes, learnt about this, but you didn't understand the consequence or the generalization of what greedy actually means, or how does it generalize to other things. Now, a matroid, as we're going to see, is going to be a construct that is, like I said before, very, very connected to the greedy algorithm in the sense that it sort of captures precisely the underlying structure for which greedy is guaranteed to be optimal for. And it generalizes beyond spanning trees, as you'll see. It's because a spanning tree is a matroid. Now, the rank function being submodular, as you'll see. Okay, so let's morph from matroid rank to matroid, matrix rank to matroid. So remember, V we're starting with matrix rank. Sorry, are there any questions about any of this? Yep.
So these are like undirected paths, right? The spanning tree is like undirected paths. Is there any consequence to that? Because there are no directed paths. I mean, there may not be directed paths with
yeah, so the directedness, well, let me first say this just in case. So the directed stuff that we're doing and adding to the graph is stuff that we're adding in order to be able to turn it into a matrix for which we can look at linear independence. But in general, what we're doing is we're not actually paying attention to the directedness, other than essentially to give us linear dependence. But then when we go back, we're finding it's the cycles in the original undirected graph. But if you were to, for example, define a matroid, there are versions of matroids that we will see. We don't see them yet. We're going to define graphic matroids, but there are other forms of matroids that can be defined from directed graphs directly. But let's first look at matroids to get a sense of graphic matroids first. Let's first of all get a sense of what a matroid is. So from matrix rank to matroid, so V is a set of column vectors of the matrix. So remember, V is our matrix, and then I is the set. I is a set of sets. Okay, it's a set of subsets of V. So every member of I, of script I, is going to be a subset of V, and then any member of I is guaranteed to be a set of is guaranteed to index a set of linearly independent vectors. Okay. And so if we have, first of all, if we have B, where B is a member of I, and so if you've got a set of independent vectors, any subset of a set of independent vectors is still going to be independent, right? We're not going to somehow, if we've got linearly independent vectors, if we take any 3 or any 7 of them or something, they're still going to be linearly independent. And so if we were to say that, which we did say, that I is the set of all subsets of V, emphasis on all, then it's basically the case that if B is a member of I, then any subset of B has to be a member of I as well. And so therefore we say that I is what's called downclosed, or sometimes it's called subclusive under subsets. So it's closed under taking subsets. So here's a way of describing it. So basically this is saying that if B is a member of I and A is a subset of B, then A is a member of I too. Now let's define this max_int function. Max_int is, we're defining as the inclusion-wise maximal independent subsets of B, or what also is sometimes called the bases of B. So what max_int B is the following. Basically, you've got, think of it again in this matrix case, you've got a set of column vectors. And these are all subsets of the column vectors that correspond to independent vectors, all subsets of the set of column vectors that we currently have. So we're currently only talking about B. So we've got this matrix, and let's take maybe this one, this one, this one, this one, this one, and that one. Okay. So maybe that set of column vectors is not independent, but maybe some subsets of them. Certainly, if you have one of them, and it's not the all-zero vector, then it's going to be independent. By definition, it's going to have a span. And then you can think about all of the subsets of that yellow set that we just drew that are independent. And so that's going to be max int. Okay, does everybody get it? Got it? So what does this mean by its maximal? Let's go through this in detail. So it's basically saying, well, first of all, it has to be a subset of B. It has to be independent. And if we take anything that's in B but not in A, so anything out of A, we're no longer independent. So it's maximally independent, meaning any addition from B loses the independence property. Where the independence property is essentially just this list or this set of vectors that have been designated just by their membership to be independent.
So B is not in I for this bullet point?
B could be or it could not be. It could be. There's nothing that says that B need be in I. What if B was in I? What would happen? B itself would be a maximally independent subset, right? Would there be any subsets of B that were maximally independent? No, because you could always keep adding stuff until you get to B again, and you wouldn't lose the independence property. So yes, B, you could have B be any subset. So B is any. That's a good point, actually. So let's just let's write this here. B is any subset. Now, one thing that we know is intuitively, we should be able to reason pretty readily that from the perspective of a linear space, when you've got a matrix, if we actually have two maximally independent subsets, or what are called two bases of B, they're going to necessarily be the same size. So this means, like, let's say that we have A1 and A2, and they're not necessarily the same, right? They don't have to be the same set, but they have to be the same size. Why must that be true in a linear space? Because again, for the same reason that we've got B and it spans some set. It's not necessarily independent, but we have the underlying space that's spanned by B. If we have two maximally independent sets and they're not the same size, it must mean that they're independent. They're not the same size. This one spans a greater set than this smaller one. So that means there's some vector in there that's not spanned by the first one. We can take it and add it to the first one and make it the same size. And we can keep doing that until they percolate up to being the same size. Right? So now we can define a rank function in this following fashion. So if we do have a particular, if we start by taking an independent set, then the rank of the independent set is just going to be equal to its cardinality. Because, right, that's the number of dimensions spanned by the vectors indexed by that set, and if they're all independent, then all of them are important. But if we take any general set, any B that's not in I, then the rank function is defined as basically the maximally independent subset. So it's the maximal independent subset, which is necessarily no greater than B. Necessarily because, well, first of all, it's a subset, it's maximal by this, and it's independent. So the rank function is the maximal independent subset of a set of indices. Now, all we're doing is we're getting this. We're sort of abstracting this away from it being a linear space. We're just listing all of the set of independent vectors in this script I thing. So the matroid question is, well, is it only matrices that allow one to define independent sets of vectors or sets of elements? I mean, maybe there are other algebraic constructs for which this kind of property would be true, and maybe there are ones for which no matrix can represent it. So that's exactly what matroids do. So they abstract. Wow, is it really this? Is it really? It's amazing how time flies. Are you having fun? Is time flying for you too? Raise your hand if you're having fun. A little bit. Oh, great! Everybody raised their hand. That's very impressive. Is all 80 million people on YouTube having fun, or all of you guys having fun? See, the problem is, in order to find out if everybody raises their hand now, I would need to do two things. One, I would need to time travel to multiple time points at the time that everybody is actually watching this, and then B, I would need to space travel, or at least Skype travel. I'd need to simultaneously Skype to all these people in the future who are watching this, and that ain't going to happen. So, all right. So let's just finish up with a little bit more on matrix. So a matroid is the thing that it abstracts the notion of linear independence. So we have a ground set, and now why is it called a ground set? We're going to, if you're wondering why, if you've heard of the word ground before, we need to talk about lattice theory, and we will talk about that. But where does the word ground come from? We'll talk about that in a bit. But anyway, there's some ground set. We don't know why it's called a ground set, and there's a collection of subsets of E. Say E is the ground set, so subsets of the ground set that we're just claiming to be independent. And there are actually lots of equivalent mathematical definitions of a matroid. But I think we're running out of time. What do you think? Should we do one definition of a matroid? Let's push forward just a little bit for one more minute. So the first thing to note is that we've got a set system. So a set system is basically the following: that we've got some ground set E, and we've got a bunch of subsets I. So E is some finite ground set, and I is some set of subsets, and we notate it in this way, where we say E, comma, script I. Now there's nothing special or important or particular about I. It's just basically we can choose any arbitrary subsets we want. So the only way to determine whether or not a given member is in I is to enumerate, is to go through and check each one. They can be arbitrarily different from each other, arbitrarily complex. They can have arbitrarily many different properties. So one useful property is the notion of hereditariness, or subclusiveness, or downclosedness. And basically what that means is, if it's the case, we've already seen this now in the case of the matrix, if it's the case that B is a member of I, then any subset also has to be a member of I. So it's a hereditary thing. It's kind of like saying, well, if you're A and B is, say, your parents, then you've inherited the characteristic of B. So basically, that's sort of a very honorable way of describing it. Basically means that you're a subset of your parents, right? And so we keep, as generations go forward, we keep diminishing in quality. So honor your parents. So we can define a hereditary system or an independent system where we say, on the one hand, it's empty set containing, and number two, it's subclusive. So this is a particularly important definition, because what we're going to do is we're going to see this side by side with the definition of a polymatroid very soon. But right now we're just talking about sets and matroids. So this is not yet a matroid. This is just called an independent system. And the reason why it's called an independent system is because anytime you've got an independent set, any subset of an independent set should be independent. Right? Why should independence seems like it should be a property of hereditariness. It's true of random variables. It's true of vectors, and anything that satisfies this thing is going to be an independent system. So these are the terms that we use for it: down monotone, down closed, or subclusive. You might encounter, although subclusive isn't used very much, but I think it's time to revive that term. It's a nice term. So here's an example. So E, the ground set is 1, 2, 3, 4, which is E. And here's a set of subsets. So is this a set system? E comma I, E comma script I. It's a set system, right? Because if what if I added 6 into one of the sets? Would that be a set system? No, right? Because it has to be subsets, right? So look in the definition. Not everything is subset. We do need to have subsets. So if we added 6 to this guy, it wouldn't be a set system. But it is a set system. Is it a hereditary system? No, because 1 comma 4 is not a member of I. Or we've got There's lots of reasons. 1, 2 is an I, but 2 is not an I. What about this? Is this a set system? Is it a hereditary system? Yes. So this is an independent system, a hereditary system. So clearly, I think that if you have linearly independent sets of vectors, then any subset is linearly independent. So a clearly linear independent set of vectors are set systems. And if you've got a graph and any forest, so any subset of the set of edges constituting a forest, not necessarily a spanning forest, is still going to be a forest. If you take subsets of edges, you're never going to add a cycle. You're never creating a cycle by removing edges from a tree or from a forest. So therefore, forests and trees are a hereditary system in the edge set of the graph. Okay, lastly, I think this is where, after we do this definition, I think we should break. So a matroid is the following. A matroid is our first definition of a matroid. We're going to see the number of different definitions, but a definition is that it has to be empty set containing. First of all, it's a set system. So you have a ground set E and a bunch of subsets of E, script I. It's empty set containing. It's subclusive, and it has this property that we've actually already seen. So basically, what it says is that if we have two independent sets I and J, actually we've seen a form of this. We have two independent sets I and J, and let's say that the size of I is 1 bigger than the size of J. Then that means that you can choose some element in I that's not in J and add it to J, and it will become independent. It will stay independent. So again, take the example of columns of a matrix. Let's say that we have two independent sets. They may have nothing to do with each other except that one is 1 bigger than the other one. So that must mean that the larger one spans at least one dimension that is not spanned by the smaller one, which means that there must exist some vector in the larger one that's not a linear combination of all of the vectors in the smaller one, and then therefore we can add that one vector that's not a linear combination of the vectors in the smaller one to the smaller set, and we haven't gotten linear independence, and we've increased the span of that smaller one. So but then this is saying that any algebraic structure, not necessarily defined by a graph or a matrix, that has this property is a matroid. Now you might think, well, is that going to do anything? So matroids were first introduced in like 1935 by Whitney, and he's one of the people whose pictures we have on the very first slide. He basically introduced this idea, and it's amazing actually. You go back and look at his 1935 paper, and you find all of this stuff there, and you find the submodular inequality there, and you find all these amazing things. But it was basically forgotten. Actually, there were a couple of individuals from Japan, and I hate to say I've forgotten their name. They also simultaneously and independently published some work on matroids around the mid-30s. But it was forgotten for about 2 decades. Nobody paid any attention to it until the 1950s, when Tutt started getting interested in that. And he said, oh, I bet there's something interesting here. And then from the 1950s, and then the 1960s, and then people like Jack Edmonds thought that there was some very important, and Jack Edmonds organized this workshop on matroids in the very early 1960s, and then it sort of created this flurry of mathematical activity on matroids. But it started out with this. I mean, this is just generalizations of matrices, or properties of matrices. Okay, so your assignment is to look at the photos and figure out who is Whitney and who is Tutt. Okay, I will see you on Monday. I will get some homework out too.